Hello, everybody. This video is going to cover 2.7 combining functions. Again, if you have any questions, make sure you text me while you're watching the video or email me. Okay, so 2.7, hopefully you're keeping up with the homework. 2.7 combining functions. So in this section, we are going to cover more of the operational things of functions rather than the graphs of them. Okay, so let's take a look at properties of functions. All right, so let's let f and g be functions. With domains A and B. So f has domain A, G has domain B. Then, number one, f plus g of x is the equivalent of doing, so this here, when we look at this is like saying add the two functions and then evaluate it, then replace all the x's with whatever is in there. Okay, so this is saying add the two functions first and then you can evaluate. Or you could do this. You could evaluate the f function, evaluate the g function, and then add those two answers together. Okay, so you could either add the two functions and then evaluate, or evaluate the individual functions and then add. Okay. Same thing with subtraction of functions. You could add the functions and then subtract the functions and then evaluate, or evaluate each one first and then subtract the results. Okay. Same thing with multiplication. You could multiply the two functions and then evaluate, or you can evaluate first and then multiply the results. And then the same thing with division. If you have f divided by g of x, you can divide the two functions first and then evaluate, or you can evaluate f function, get an answer, evaluate the g function, and then divide. All right, now for these here, these first three functions here, the domain is going to be the intersection of A and B. So waiting for the A, there it is. So the intersection of A and B, which means that it's all of those numbers that A and B have in common. Okay, so let's say F has the domain 1 through 10, and B has the domain 1 through 9. Okay, so then the domain, if you add these or subtract these or multiply these, then the domain is going to be the intersection of those numbers. So if A is made up of 1 through 10 and B is made up of 1 through 9, then the only numbers that they have in common are the numbers 1 through 9. So that would be the domain. Okay, it's made up of the numbers that they both share. Okay. For this last one over here, the domain is also the intersection of A and B. However, when we look at A and B as individual functions, that's fine. But then here, because we're doing division, we now have G in the denominator and we don't want 0. Okay, so because then we get undefined. So the domain is going to still be the intersection of A and B, except where G of X equals 0. Okay, that way we don't get undefined. All right, so let's take a look at some examples here. All right, so let's suppose that we let f of x equal x squared plus 2x. And let's let g of x be the function 3x squared minus 1. Okay, so we have here two functions, f and g. Okay, when we look at f here, we don't have any sort of restrictions on x. We can choose a negative number for x. We can choose a positive number for x. We can choose 0 for x. And we will still get a real answer. So the domain here, the domain for f, is all real numbers. There are no restrictions on what we can use. Okay, so I'm going to use that boldface R. Same thing with g. So when we take a look at g of x, we see that there are no restrictions. So over here, the domain for g is also going to be all real numbers. And again, here I am going to use the boldface R. Okay, so let's take a look at these operations with these functions. All right, so let's find the following. All right, so let's go ahead and do f plus g of x. Okay, so no particular number to evaluate the function at just yet. Okay, so this means to add the two functions together. Okay, so that's going to be x squared plus 2x. That's your f function, right? So that's your f function, and we are going to add this function. This is your f function, and we're going to add that with our g function, which is 3x squared minus 1. Okay. And removing the parentheses and then combining like terms, we get 3, 4. Well, here, let me go ahead and remove the parentheses. I'll work this out step by step for you. All right, so so we have this here. Okay, and now we can go ahead and combine like terms. So we get 4x squared plus 2x minus 1. Okay, so this is our new function, and we see that there are no restrictions here. And the domain is going to be the intersection of the domain for the domain for f and g. So if we look at the domain for f, it's all real numbers. The domain for g is all real numbers. So what do they have in common in their domains? Well, it's all real numbers. Okay. Let's take a look at this one. So this was an example where you were adding two functions, but not evaluating at any particular x value. Okay, so let's take a look at this one. F plus g of 2. Okay, So if we take a look at this one here, then there are two ways to go about this. Okay. We'll look at method 1 here. And we'll look at method 2 over here. Okay. And these two methods will be based on the properties that we just listed above. Okay, so the first one says that, oh, okay, well, the first method says, oh, well, I could evaluate at 2 and then add them. Where's that plus sign? There it is. Okay. All right. So I can do that. So if I do this, evaluate the f function and then evaluate the g function and then add our result together, then that means here, plug into the f function and I get 2 squared plus 2 times 2. And if I evaluate the g function, then I get 3 times 2 squared minus 1. And so here I get 4 plus 4 is 8. And here I get, you got to do exponent first. So 2 squared first and then times 3. So 2 squared is 4 times 3. So exponents first, then you can multiply. So 2 squared first and then multiply by 3. So we get 12 minus 1 is 11. So here we get 19. Okay, so that's method 1. Evaluating f, evaluating g, and then adding the two results together. Method 2 is says this is the one where you could add the two functions first and then evaluate at 2. So this is like saying x squared. Let me wait for it. This is like saying x squared plus 2x. That's your f function plus your g function, right? And then combine like terms, and we get 4x squared plus 2x minus 1. And then we evaluate it for x equals 2. So let's go ahead and plug in 2. And we get 16 plus 4 minus 1, which becomes 19. So we see here that it doesn't matter which method you use, whether you evaluate the individual functions first and then add their answers, or add the two functions first and then evaluate at 2, you get the same answer. Okay? All right, let's take a look at another example. Okay, so let's do g minus f of -1. Actually, let's just do +1. Waiting for it. There it is. Okay, so choose whichever method you want. If you want to pause right now and try it on your own and then press play when you're done to see if you get the same answer, go ahead and pause the video. Okay, so you should have gotten -1. Okay. Um, let's take a look at another one. Let's take a look at f times g of x. Okay, so here again, no particular x value to evaluate the functions. So we just need to take the two functions and multiply them together. So if I have x squared plus 2x and then times 3x squared minus 1. Okay, so then here I get 3x to the fourth minus x squared plus 6x cubed minus 2x. Okay, I like to have them in descending order, so I will start with the highest exponent, x to the fourth, and then the next one, which is x cubed, so plus 6x cubed, and then minus x squared, and minus 2x. Okay, so again, over here, there is no particular x value to evaluate for, so this is as far as we can take this problem. So if you don't see a number there, you're just doing the operation and not evaluating. All right, let's take a look here. Let's do a division one. That way you can see what I mean about the domain. All right, so let's do, what was that? Was that C? That was D. Okay, so example E, suppose that I have these two functions that I have to divide. All right, no particular x to evaluate it for, so I am going to have x squared plus 2x in the numerator. That's my f function. My g function, 3x squared minus 1, will go in the denominator. Okay. Okay, so no particular x to evaluate for, so we just leave it like this. And if in the homework or on a test, if it asks you for the domain of this function, well, we already know that the domain of f is all real numbers. We know the domain of g is all real numbers. And so here, the domain here is going to be, remember, it's going to be all real numbers except for where that denominator would be 0. So right here, I want to find out where does this denominator equal 0. So let's go ahead and solve for this. 3x squared minus 1 equals 0. So I add 1 both sides. So I get 3x squared equals 1. And then I'm going to divide both sides by 3. So I get x squared equals 1/3. And then we need to take the square root of both sides. Okay, so we need to take the square root of both sides to cancel the square. But remember, when you take the square root, you end up with a plus minus. So we end up with plus minus 1 over square root 3. And if we rationalize this, we get plus or minus square root 3 over 3. Okay, so that's where the denominator equals 0. So here we're going to say all real numbers except, so I'm going to have that minus sign, except, and then in here in my curly brackets, I'm going to list all the numbers that I want to exclude. So I want to exclude positive square root 3 over 3 and negative square root 3 over 3. Okay, I will just go ahead and write it like this. So these are the numbers that are not part of the domain, because if we use it, we end up with 0 in the denominator, which makes this undefined. Okay. All right, so let's take a look here. If you're wondering about this right here, what I did was I rationalized the denominator. So what that means is, okay, so right now in this first answer here, we have square root 3 in the denominator, right? And square root 3 is an irrational number. So what I do is I do something to this number so that my denominator becomes a rational number. So that's why we call it rationalizing the denominator. We take an irrational denominator and we make it rational. Okay? Don't you wish we could do that with people? Okay, so let me show you just a quick lesson on rationalizing. So I'm going to leave off the plus minus for now. So over here, I have this here. And so the denominator is irrational, square root 3. Okay, so if I want to rationalize the denominator, then what I end up doing here is waiting for my red pen. Okay, so what I end up doing here is, so 3 is not a perfect square, right? If it were, then we wouldn't have this irrational number in the denominator, right? If we had, like, say, 9, right? Square root 9. Well, square root 9 is 3, right? Or if we had square root 16 or square root 25, right? We could simplify all of those. But this here, square root 3 is not a perfect square. So if you punch that into your calculator, you get this never-ending decimal. All right, so what I want to do is turn that 3 into a number that's a perfect square. So this is what I'm going to do. If I can turn that into a 9, that would be great, right? So that's what I'll do. So I am going to multiply by 1, but 1 written in the form of a number over itself. Okay, so I'm trying to make that bottom a perfect square. So I'm going to try to make it square root 9 instead. So I'm going to multiply by square root 3 over square root 3. And what happens here is I get square root 3 in the numerator, but look what I get in the denominator. I get square root 9, which is a nice perfect square. So here in the numerator, I get square root 3. And then in the denominator, I get square root 9. Okay, but what is the square root 9? Square root 9 is 3. Okay, so hopefully you're quick at rationalizing denominators like these. If you took trigonometry, you did that quite a bit with sine, cosine, tangent. Okay. All right. Okay, so enough about that. Let's go ahead and take a look at composition of functions. Okay, so composition of functions. So this has a completely different notation. So we have your 4 basic operations: addition, subtraction, multiplication, division. So we looked at how to add, subtract, multiply, and divide functions. So we have another operation called the composition of functions. Okay, and we use a little circle for the notation. So it looks like this. Okay, so it looks like this, F circle G. So it's this little circle, and that's actually how we read it, F circle G. Okay. So that means the composition of functions. Sometimes it's written like that. Sometimes it's written like this, F circle G of X. Okay. So be aware of the notation. So what this means is this. It basically means take the G function and you evaluate F using the G function. Okay. So maybe your G function is X plus 1. So that means you're going to replace all the X's in F with X plus 1, with whatever your G is. Okay. All right. So, okay. So the domain. So what happens is we have these three functions. You have f of x, we have g of x, and then you have the composite function, the function composed of these two. Okay, so we have f of g. Okay, so what happens is when we're trying to find out when we're trying to find the domain of the composite function, okay, this here, we want to know the domain of this final function, right? What happens is we have the domain of G, okay? Okay, so we'll be able to know what that is. And here, the domain of this final function is what we want to know. Okay, so over here, the intersection of these two okay, so this one over here, let me do this. Hold on a second. Let me get my eraser going. So what happens is here you end up with a domain of like a final function, right? So let's say that when you do the composition, you end up with like, let's say you get x plus 1, okay? Well, then the domain of that final function is all real numbers, right? Okay, so what happens is, okay, so you end up with the domain of your, I don't want to call it F because we already used F. So final function. Okay, so you look at that, whatever expression you have at the end there, and you look at it and you determine its domain. Okay, but then you look at the domain of G, the one that you're plugging in. Okay, then the domain of the composite is going to be the intersection of the domain of G and the domain of the final. Okay. That's supposed to say final. We're waiting for it. There it goes. Okay. So that's going to be the domain of the composite function. So basically, look at your final function, figure out its domain. Okay. For the most part, if there were no restrictions over here for G, the function that you plug in, if there are no restrictions there on the domain, then this one over here will be your domain. Okay. So whatever you have here, that will most likely be your domain. But you look over here to the D of G just to see if there were any restrictions that you also need to include at the end. Okay. All right. So let's take a look at some examples. All right. Let's suppose that we have this function for f, 2x plus 3. And let's suppose that g of x is 4x minus 1. Okay. So here, when we look at these, the domain here is all real numbers. There are no restrictions, no fractions, no square roots. Okay. And then same thing over here for G. There are no restrictions. So the domain here is also all real numbers. Okay. So what we're going to do now is we are going to find the following. We're going to look at F circle G. We're going to find G circle F. And we will look at F circle F. Okay. F circle F. And we will also look at G circle G. Okay, so we're going to do the composition, all of these 4 compositions, but we're also going to find their domains. Okay. All right, so this is starting to slow down. Okay, so up, up, there we go. All right, so let's start with the first one, F circle G. Okay, so this means that we are going to be evaluating F function by plugging in the G function. Okay, so what is the G function? Well, the G function is 4x minus 1. So instead of writing it like this, what I'll do is, because that looks a little abstract, so instead of writing g of x, I'll write down what g of x actually is, which is 4x minus 1. Okay, so let's go ahead and write 4x minus 1 in here so that we know what we are replacing all the x's with. Okay, and again, this here okay, tells me what I'm going to replace all my x's in F with, okay? And it tells me that I'm going to replace all the x's in F with g of x. And g of x is 4x minus 1, okay? So I'm going to replace all the x's in F. Remember, x is 2x plus 3. So I'm going to replace that x with 4x minus 1. So instead of writing 2x plus 3, I'm going to write 2 times 4x minus 1 plus 3. Okay? Because remember, whatever is in here is what you're going to replace the x's with. Okay? So that's why over here, the f function says 2x plus 3. So I replace the x here with 4x minus 1. Okay, so let's go ahead and work that out. 8x minus 2 plus 3, and that gives us 8x plus 1. Okay. All right, so we get 8x plus 1, and we want to figure out the domain. So when we look at this 8x plus 1, there are no restrictions here. So here, there are no restrictions. So far, the domain here is all real numbers. But remember, we have to look at the g function, the one that got plugged in. So we plugged in g, so we need to look at the g function to see if there were any restrictions. Were there any restrictions? No. Okay. So no restrictions in G, no restrictions here. So your domain for F circle G is going to be all real numbers. Okay. Let's go ahead and do B. B is G circle F. So now this is saying take the F function and plug it into the G function. Okay, so instead of writing f of x, let's actually write down the function. So f of x is actually 2x plus 3. So we are going to do g of 2x plus 3. Okay, because remember, f of x is 2x plus 3. Okay, so this now means that I have to replace all the x's in G with 2x plus 3. So G is 4x minus 1. So instead of writing 4x minus 1, I'm going to write 4 times 2x plus 3 minus 1. Okay, so you are replacing the x's in G with 2x plus 3. Okay, so we get 8x plus 12 minus 1. So I get 8x plus 11. Okay, hold on. Did you just find the mistake? All right, it's getting late here. All right, you should have seen this mistake. Where is my function? All right. Oh no, actually you were fine. Okay, I'm looking at a different problem. Okay, so we replaced all the x's. Let me just look at my functions. Okay, so I plugged in f into g, 4 times 2x plus 3 minus 1. Okay, good. So this is all correct. So this here is 8x plus 11. So the domain in this case is all real numbers. And the function that we plugged in was 2x plus 3. And the domain for that is also all real numbers. So there are no restrictions for both of them. So D, G circle F is all real numbers. Okay, not sure why my writing is not coming up. Abracadabra. Okay, so right here, the domain, all real numbers, because there are no restrictions. The function that we plugged in, this one, right over here, no restrictions. So the domain of this one was all real numbers. Okay, so what you're looking at is the final function and the function that you plug in. Okay, so both of these, domain is all real numbers. So the domain of G circle F is all real numbers. If there's any restriction here, if there are any restrictions between these two, then that's the restriction you also have to include in your final answer. Okay? All right, which one is next? F circle F. Okay, F circle F. Okay, so F circle F. Okay, so that is the same thing as saying plug the F function into the F function. Okay, so that means we are going to plug in 2x plus 3 in for all of the x's. So 2x plus 3. Okay, so f of x is 2x plus 3. Okay, so that's what I want to replace all the x's with, 2x plus 3. Okay, so I'm going to write 2 times 2x plus 3 plus 3. Okay, because I replaced all the x's in f with that. Okay. All right, so let's go ahead and multiply this out. We should get 4x plus 6 plus 3. Okay. And so we get 4x plus 9. So here we see that we don't have any restriction. We don't have any we don't have the fraction. We don't have square roots. So here the domain is all real numbers, right? And then also right here, the domain is all real numbers. Waiting for it. Okay, so both of these, the function that got plugged in, 2x plus 3, all real numbers, and the final function, 4x plus 9, the domain is also all real numbers. So the final domain of df circle f is going to be all real numbers. Okay. All right. For letter D, I'm going to let you do that on your own. Okay, so G circle G. You should try it out on your own. And I'm going to write the answer right now. But go ahead and try it on your own. Pause this and then check back to see if you get the same answer. Okay, hit the pause button. Okay, and the final answer, you should get 16x minus 5 over here. And your final domain of G circle G is going to be all real numbers. There were no restrictions. That's supposed to be a 5. Hold on a second. 16x minus 5. Come on. This thing is kind of glitchy. Okay, a lot glitchy. Okay, 16x minus 5. All right, so that is about it. Do you want to see one where there are restrictions just to see what I mean? Okay, so here's one last example. Let's suppose that we have these two functions now. Suppose we have this one for f of x, and suppose that we have this one for g of x. Okay, and let's just do let's do f circle g. Okay, And before we do that, let's take a look here. This one here has a domain of all real numbers except for 0. This one here has a domain of all real numbers. Okay, right? Because x, we can't have 0 in the denominator or else we get undefined. Okay, f circle g means f of g, which means we are going to plug in the g function into the f. What is the g function? It's 2x plus 4. Okay, so we're going to take that 2x plus 4 and plug it into the f function. So we're going to replace all the x's with 2x plus 4. So I get 1 over 2x plus 4. Okay. All right, so now we want to find the domain. So we need to look at the function that we plugged in, and we want to look at the final function that we got. Okay, so over here, the one that we plugged in, no restrictions. Domain is all real numbers, right? Okay. This one over here, our final function, 1 over 2x plus 4. We have this fraction, so we have to be careful because we don't want to end up with 0 in the denominator. So what would make that denominator 0? Negative 2, right? Negative 2. If we plug in negative 2, we end up with negative 4 plus 4, which is 0, 0 in the denominator. Okay, so here the denominator of this final one is all real numbers except for negative 2. Okay, so once you look at the two functions here and their domains, the one that we plugged in, this one over here, has a domain of all real numbers. The final one over here has all real numbers except for negative 2. So the final domain is going to be all real numbers except negative 2. Okay, so it's basically you have to take a look to see if you have any restrictions from either of these two. Okay, if you have a restriction here in either of these two, then you have to include it in your final answer for domain. Okay, so that's an example. Okay, so if you have any questions, make sure you text me or you email me or you request a Zoom office hour. Other than that, we are done. So enjoy the rest of your day.